Welcome back to the multi-agent learning course on the replicator dynamic. This is part 2 on the replicator dynamic. We will now discuss the origin of the discrete replicator equation. And the discrete replicator equation is important because you will have to implement it in your programming assignment. So better check this part of the presentation. So the discrete replicator dynamic is caused by the discrete replicator equation, and the discrete replicator equation is stems from the discrete step equation. And the discrete step equation is given by the number of, so not a proportion, but the number of individuals if type I in the next round. So we're talking about the discrete number of rounds, and we are left the idea of a continuous replicator equation, so time proceeds in steps, is equal to the same number of participants. We're talking about the number of participants, same number of participants, plus a constant number of participants that are due to birth and death. So given a number of participants, a number of these participants will give birth to other individuals of type I, and a number of these individuals of type I will die. And that number is incorporated in the birth and death rate, which is a constant. And then this part is responsible for the variable percentage that is added, subtracted due to fitness. So it is important to emphasize right at the outset that although the speed of the dynamics is influenced by this parameter, the properties are not. Only the speed. So the dynamics is exactly the same if you leave out this portion. And if you leave out this portion, you will arrive at the formulation of the replicator dynamics on the bachelor course slide. So if you surf to the bachelor course slide, the old practicum assignments, here, comparing strategies. Well, this link is given in the previous presentation on the bachelor program assignment, so I will go through this rather quickly. So you see here also a formulation of the replicator dynamics, but it is without birth or death rate. So I won't explain notation here, but this is the same but without birth and death rate, because this version of the replicator dynamics converges faster. If you involve birth and death rate, the dynamics is slower. And it is also the replicator dynamic given by Jolan in his assignment document on the programming assignment is without birth and death rate and without this constant factor. But then you have to make sure that these numbers are positive. You have always to ensure that, to prevent negative proportions, which don't exist obviously, and a certain extermination of species, it is required that this number here is always positive. And if not, you can guarantee that by adding birth and death rate beta, hence the beta. So if scores of reply rules in your matrices are negative, you must add a positive number in order to prevent that negative proportions will ensue. I noticed that this requirement of not to have negative proportions due to the right fitness measure is often left implicit in the literature. Now you can calculate now the absolute growth of species, the delta QIT, just by subtracting those two, and well, just filling out the definitions of QIT plus 1 minus QIT, and you will arrive at the delta, so the change of, and we need this for later. Recall that the QI are not proportions but numbers, number of participants, so the QI do not add up to 1. Now this is the discrete replicator equation, which follows from the step equation, and we will show that in a moment, or I will refer to the proof. I will not go into length to you with the proof. So you can use this equation for your programming assignment. So the proportional species I at the next round, in the next round, is equal to this proportional species I in the current round times, well, if you leave out this, if your payoff matrices only contain positive numbers, then you can leave out this, times the fitness of species I divided by the average fitness. That's a discrete replicator equation you can use in your programming assignment. So the idea of the discrete replication is between two generations, an individual of type I produces this much of offspring, where beta is the intrinsic birth and death ratio, and F sub I is the fitness dependent birth ratio. Now, the discrete replicator equation follows, so this is not a definition, this equal sign is not a definition, follows from the discrete step equation. So the discrete step equation, that is a definition. So in order to understand the replicator equations, it is enough to understand the intuition behind this equation, because the rest follows. Next slide. So this is a derivation of the discrete replicator equation from the discrete step equation. Blatantly said, or a bit mundanely, or what is it? To sum this derivation up, fill out the definitions of, well, this is the definition of pi t sub 1, fill out all the, it's just a basic filling out exercise. QIT plus 1 is defined as QIT plus, fill it out, cancel terms that cancel each other out, and you end up with the discrete replicator equation. So I'm not going through you with this. You can check it out yourself if you really suspect it's not true or something like that. Let's move on to the next slide. So if a species is an important property of the replicator equation is, very important property, that if a species is present, it was always present and it will always be present, and the same for absent. And this can be proven, well, there's not a proof, the proof amounts to just by looking at the discrete replicator equation and recalling that those numbers are always positive. So you effectively, so this number is positive, and therefore this number is positive, and therefore the whole fraction is positive, and therefore you're always multiplying by a positive number, and the result immediately follows. So if the proportion was absent, it remains absent, and if a proportion was present, it remains present, and it was present. And you see that here. So fixed points of the replicator are always corners, and if only one species is absent, for example here at the bottom, there the third species is absent, then it will remain absent. So the dynamics, once it is on an edge, it will remain on the edge. You see it also here. If a dynamics is on the edge, it will remain on the edge. If dynamics is on the edge, it will remain on the edge. Of course, you can have fixed points on the edge, but it will remain on the edge nevertheless. Next slide. Yeah, well, this is just an extension of the dynamics. And well, the same holds for the interior. If a point is in the interior, it remains in the interior. So all these points converge to the edge, but it will never be on the edge itself. So if a point is in the interior, it will remain in the interior. And you in your practical assignment should always start with proportions that are in the interior. Because if you arrive at a well, if you converge at a point, then that point definitely is a Nash equilibrium, as is here. So you know if you start in the interior and if you converge, then you know for certain that the limit is a rest point. That's one. And you know for sure that the rest point is a Nash equilibrium. Now another simple claim is if that the species I grows if and only if its proportion is of course non-zero, of course, and it has above average fitness. We already intuitively saw that, but now you can just derive it with the discrete replicator equation. Well, if it grows, then this is the case. We'll just apply the definition of discrete replicator equation. Cancel out, well, divide by this one because this one is positive. So now you use this assumption here. Divide by pi sub t, p sub it, and then you have this one cancel out equal terms, and you indeed have this one, provided the proportion is non-zero. And these implications hold both directions. Dus they really hold both directions, so not one direction. So you should check that you can reason the other way around, provided this is the case. Now, what is the effect of the beta? What, for example, if beta is large, well then the dynamics will be slower. So it is recommendable to adopt a small beta in your program, in your program assignment as possible, without making the payoffs, without making the entries in your replicated matrix negative. So if you have negative payoffs in your ground table, you should add these payoffs with some positive number so that they become non-negative. And if they are non-negative, then you can apply the replicator dynamic. So how does the continuous replicator equation follow from the discrete replicator equation? Well, the idea, I just convey the idea, not to give the whole derivation, to reduce the time steps into smaller time steps, because we are talking about continuous replicator equation, delta. So smaller time steps. And the idea is that per time step, the largest part, 1 minus delta, remains the same. So QIT plus delta is 1 minus delta. For the largest part, it remains the same. And for a small part, we apply the discrete replicator equation for very small delta. And we obtain the continuous replicator equation if we let delta go to 0. And if we set delta to 0, not let it go to 0, but if we set 0, nothing happens, you see. And if delta is 1, if delta is 1, we get the discrete replicator equation in full. Next slide. So these slides amount to the derivation of the continuous replicator equation from the discrete replicator equation, which is letting, well, this is a limit argument, so the change in the proportions is the derivative with respect to delta, and then letting delta to 0 go to 0. So you end up with this equation, and then filling out the right terms and cancel out other terms, you arrive at a variant of the discrete replicator equation, but then with delta. And you fill out all the, so here you fill out what you have here, just derived, and then do some high school algebra, and then you end up with this. You fill out all the terms and you end up with the continuous replicator equation. So for non-believers, you can check that the continuous replicator is a result of the discrete replicator, and the discrete replicator is a result of the discrete step. Now, for a long time, I didn't know myself that you can just explicitly calculate stationary points of the replicator. So in a way you can calculate Nash equilibria, because all Nash equilibria are stationary or rest points, and some of them aren't, but you can just reduce your search of Nash equilibria to the rest points of the replicator. So you can actually calculate the stationary points of the replicator. This is not much discussed in the literature, probably because it's so evident, but I didn't find it evident. And I just very lately discovered that you can simply just calculate them. So let's do that with an example. So you have the replicator with 3 species, x, y, and z. Sorry, x, y, and z. Well, let's modify that immediately. So x, y, and z. And well, to find all the stationary points or fixed points or rest points, which or steady state is the same, we have to set the replicator dynamic to 0. So the change in the x coordinate for the first species is 0, the change for the second species is 0, for the third species is 0. So for which x, y, and z is that the case? Well, we have to have x, y, and z in the 2 simplex, which is to say that there must sum up to 1 and larger than 0. And the first equation says x is 0. Well, it's a product of if a product is 0, then either of the 2 factors must be 0, or both must be 0. So the other factor can also be 0, and this amounts to a polynomial with 3 variables. So this polynomial in itself is not easy to solve, also in combination with the other polynomials. So this is a system of equations, and of course you can't solve this by hand. So use Maple, Mathematica, or SciPy, or another scientific computation library, and you will find that the following are rest points. Well, of course you will always find these, because the corner points of the simplex are always rest points, of course. And then you will find 3 other rest points, of which one is or which two are a Nash equilibrium. So this rest point is not a Nash equilibrium. How do I know? Because I entered this game in Gambit and let Gambit compute a Nash equilibrium, and Gambit only finds 3 Nash equilibria. So both results require external means to get an answer. So Gambit for the Nash equilibria, and I used Mathematica for solving this system of equations to find the rest point. Okay, so you can actually, in order to find Nash equilibria, you can compute Nash equilibria yourself by computing the rest points and then cancelling out those that are not Nash equilibria, because you can check them by hand that these are not Nash equilibria. So you can cancel them out and you are left with the true Nash equilibria. So this is a way to compute Nash equilibria. Also of more sophisticated games or high dimension games. So this is the phase space of the replicator as discussed in the previous slide, and you see that some rest points are not Nash equilibria. The circled rest points are Nash equilibria, and the circled rest points are found with Gambit. So I did not compute them myself. So NetLogo simulation calls Gambit and then it applies the open circles around the rest points. Sorry, next slide. So previously I gave some results, but it is difficult to obtain an overview of all those results and interconnections and so on. First, look at the color of the nodes. The blue nodes refer to game theory. So this node here refers to strong Nash equilibrium. Sorry, strict, which is something else. Strict, not a weak, but strict. Strict Nash equilibrium. Strong is something else. Strict Nash equilibrium, and this blue node refers to Nash equilibrium proper. And so the blue nodes refer to game theory. The nodes that are colored in olive refer to evolutionary game theory, which we did not have discussed and we will not discuss in this edition of the course. Well, we're talking now at 2020, maybe next year, but this year we don't. So this is evolutionarily stable strategy and this is neutrally stable strategy, but we didn't discuss those concepts. What's important for us is that we know that all Nash equilibria are fixed points of the replicator. So the green nodes refer to replicator dynamic. So the dynamic, the behavior of the replicator. So we know for sure that all Nash equilibria are fixed points or rest points of the replicator. And we have to find Nash equilibria among the fixed point of the replicator. That's another way to put it. We also know that if you can prove that a rest point is Lyapunov stable, then it is a Nash equilibrium. So Nash equilibrium are between Lyapunov stable states and rest points. That's important. And this diagram also shows that interior limit points of the replicator. So if you start with proportions in which all species are present, then you have an interior point to remain interior, and if it converges, then you know for sure you have a Nash equilibrium. So if you apply the replicator dynamic to the ground table, always start with proportions in which every species is represented. Because if you have convergence, then you surely know you arrive at a Nash equilibrium. Okay. Sorry. So this peculiar result, a limit point of the replicator is indeed a fixed point of the replicator, is not self-evident, but it has to be proven. So you think if the replicator dynamic converges to a fixed point, converges, then what it converges to must be a fixed point. And yes, that's indeed true. So if a replicator dynamic converges, then what it converges to is indeed a fixed point. That's the arrow here, and it's proven in Weibull. And here, it's proven in Weibull. And here are the other justifications of all the other implications. So I just named a few sources: Weibull, or Schoem and Leighton Brown, or Herbert Gintis. The sources I referred to are mentioned here. And Weibull, especially Weibull and Hofbauer and Sigmund, are authoritative sources on evolutionary game theory. And I guess that's it. So thank you for bearing with me. I hope you can use some of this information or all of this information for your programming assignment. And hope to see you next week on the discussion of alternative approaches to evaluating and comparing multi-agent learning algorithms. Work of Bernard Bouzy, Ario and Associates, and Zawadzki and Associates. Thank you.